So hello again and welcome to Ironcast. This is our second video. We're talking about functions. And so today we're going to do two things. We're going to talk about how we can express relations, like different ways of writing a relation, writing or drawing a relation. And then discrete and continuous functions, okay, what these kind of functions are and the difference between the two. And then domains, codomains, and range, we are not going to do it today. I don't think we have time. So we probably will put it in the next video because this is an important thing when you go even into A levels or calculus classes in university. So it is an important idea. At the same time, I want to have like some maybe a bit more examples and so on, so you can have fun with it. Definitely you can skip through the video if you're only studying for SPM purposes and things like that, but more examples help you to understand it better, so I'll just keep it in another video. Okay, so today we are going to study relations. Now so the most common way of expressing relations, we have seen in the last video also, is arrow diagram. I mean, the most common way that we have used so far. Okay, because after this I would say the most common way is going to be the graph. Okay, so let's try drawing an arrow diagram and then we can move from there. So we saw a relation, and then let's take one more today. Maybe this relation has 4 inputs and 4. Okay, and then here we have 10, 20, 30, 40. Okay, and how these things are linked, 1 goes to 10, so this is a very simple relationship. But 2 has, this input 2 has 2 outputs. Okay, and then 3 and 4 share the same output, which is 40. Okay, so let's break it up. First we have this relation, which is pretty much a 1-to-1 relation. Okay, so this is 1-to-1, and then this one is a bit tricky. Okay, we have 1 input but 2 outputs for it, so this is the case of a one to many. Okay, and this is where the problem is, right? We explained this in the last video, where you cannot have one input with 2 different outputs. So this is where the problem starts, and then this means our relation is not a function. And by the way, what is our relation here? See, we have an example of a one-to-many case, and then we also have another example of a many-to-one case, right? Which is this side here. Okay, we have more than one input that goes to the same output. This is not really a problem. Okay, this is not really a problem. It doesn't mean that it cannot be a function. Our problem is with the green color group. Okay, the green color group where it says where it's a one-to-many relation. So now this entire relation as a whole is a many-to-many, because it has both a one-to-many and many-to-one, right? So this is a many-to-many, and it's not a function. Okay, it's not a function. Cool. Now we can write this thing in different ways. So another way for us to write it is just through some coordinates. Okay, we can express each relation as each individual arrow as a coordinate, and then we can put all of this in a set. So let's open the set first. Okay, we have our brace. Okay, so we have our brace. Okay, and then let's do it by color. So our pink color relation is one that has an input of 1 and output of 10. Okay, so this is how you write the coordinate. You put the input on the left and then a comma and then the output on the right and close it by brackets. Okay, it's a coordinate. The x coordinate is the input, the y coordinate is the output. Okay, and then we said put a comma. What's the next group? The next is the green group. So the green group has two arrows, right? The first arrow is 2 to 20 and the second arrow is 2 to 30. Notice that this is telling us that, you see, both have the x coordinate, that is 2. So we have the same input in both cases but different outputs. And then the third case will be 340 and 440. Okay, notice that here the inputs are different but the output is the same. Okay, then you close the set because these are the only lines. So you can recheck. We have 1, 2, 3, 4, 5. So we should have 5 arrows here. And yes, we do have 5 arrows. So now this is writing in terms of ordered pairs. You don't usually use this in many places. So I would say this is the least used. Okay. But now let's think about a graph, and the graph is probably the most used. It's very common. So we have 4 inputs, 1, 2, 3, 4, and most of the time we put our inputs on the objects on the x-axis, okay, the horizontal axis, and then outputs on the vertical axis. Okay, so we have 10, 20, 30, 40. Okay, so oops, it's okay, let's use black. Okay, so we represent each relation by a dot, a point. Okay, the point, you take the, you look at where the input is and where the output is, and then you draw a point there. So this is our first point, which is at 110. Our second point is at 220. So 2 is the input and then 20 is the output, somewhere here. The third point has the same input but a different output, which is 230. And then we have 2 more points. Okay, both have the same output. So one is here, the other one is here. Okay, so we have, in this case, we have the same, 3 and 4 have the same output. Okay, now let's break this into the groups that we colored just now. So this is our pink group, right? The 1-to-1 relation, there's only one dot. Then this is our green group. So this is our many-to-one, one-to-many relation. Okay, and this is the problem. So we know that one input can't go to 2 outputs. So if you see a vertical set of points like this, then this is not a function. Okay, because this is the part where you get a one-to-many relation. Okay, and then the third and final one is this part here. Okay, this is our many-to-one relation, right? We have 3 and 4 as inputs, but we have a same output. Okay, and this is not really a problem. It's not something that tells us it cannot be a function. The real problem is in the green group, where you have one input but 2 outputs. Okay, so idea here is that if you look at a graph and people want to ask you whether this is a function or not, you look at these vertical points and you can say that this is not a function. At the same time, I want to stress that these horizontal points, like these two, this golden group here, these horizontal points, these are not a problem. If they are horizontal, they are not a problem. Okay. The reason they're not a problem is because we have already justified last week how it's okay to have multiple inputs with the same output, but not the other way around. Okay. Cool. So now let's go to our second topic for the day, which is discrete and continuous functions. Okay, so discrete just means a discrete function is one where I have a finite, or I can count. Okay, finite means I can count number of inputs. Okay, I can count the number of inputs. So I may have, let's just look at the previous example. This is a good one. So how many inputs do I have here? I have 1, 2, 3, and 4. So there are only 4 inputs, right? There's nothing else. So that is a finite number. 4 I can count. I can say that there is exactly 300,000 inputs for some function. Okay, and that is also finite. Okay, 300,000, although it's a big number, it is still a number. Okay, you can still count. It's 300,000. So that is still a finite number of inputs. Okay, so as long as you can count the number of inputs, then the function is discrete. So let's put it on a graph. Okay, say I have only 3 inputs. Okay, 1, 2, and 3. Or let's be a bit more general. Let's say A, B, and C. Okay, so it can be any number. Okay, A, B, and C. And then only these 3 inputs, and maybe this output is here, this point is here, and this point is here. Okay, so if we look at the y-axis, we will know that okay, this is the output for C, this is the output for A, and this is the output for B. Okay, cool. Okay, so we have 3 points and these are the outputs. So this is how a discrete function is. Okay, notice that we don't have any points, we don't have these points. Okay, we don't have a point here, or anything like that, because at all these inputs are all, oops, I think, yeah, so all the blue inputs are irrelevant. Okay, so there's no such thing as there's no image for the object, say like this object, which is maybe C plus 1. Okay, because C is here, so maybe this is C plus 1. There's these values and all are not in the inputs. Like we're not considering them. Okay, we don't care about them. Okay, we don't care about this, we don't care about this, we don't care about this. Okay, so you don't have all these points. Okay, all these don't exist, so we only have 3 dots. Okay, that is this, and this. Okay, cool. So point is, discrete functions, you will see points in the graph. Okay, here we have 3 points. For continuous functions, okay, it's usually the case that we have a range, an interval of inputs. Okay, so maybe like okay, so I'm taking all my inputs to be any number, all the numbers between, so I'm taking all the numbers between and including maybe from 2 to 5. Okay, as my inputs, any number in this range. Okay, And may I ask how many numbers are there between 2 and 5? You cannot count. Okay, there are just so many numbers. Like there's so many decimals. There is 2.5, 3.565, 7.32872. Whatever number that falls in the range is inside, is an input. Okay, so this kind of thing is a case where you have an uncountable number of inputs. Okay, or we also say that where you have intermediate values. So the word intermediate here just refers, you have intermediate values. So the word intermediate here comes from the fact that, so let's just take a simple way of dividing this interval that we have here. Okay, it's numbers between 2 to 5. So maybe let's take the integers. So we have 2, 3, 4, 5. Okay, we have 4 integers in between, but we can break this into smaller groups, right? Like 2 and 3, we have 2.5 in the middle. So there's 2, 2.5, 3, then 3.5, okay, 4, then 4.5, then 5. But this we can also break into a smaller division. Okay, you see all these points are inside the range, I mean the interval. All these points are inside the interval. So the point is we can find bigger, I mean smaller and smaller and smaller and smaller divisions where we I mean that will have points inside the interval, right? Like here we can break it even further into 2.25, then 2.5, then 3, and so on. So then we can go even further. We can break, like we can halve it again, 2.125, and so on, right? So we can always get smaller and smaller and smaller intervals. Okay, and we'll get a lot of decimals, whole lot of decimals. So there are always intermediate values. There are values inside the middle. That's what it's trying to say. You take any two numbers, there is a value in the middle of the two, such that that value is also inside your interval. Like you take 2 and 3, there's 2.5, right? Then if you take 2 and 2.5, there's 2.25. If you take 2 and 2.25, there is 2.125. So you can always get some number, okay, in the middle, such that that number is also in our, oops, that number is also in this interval. Okay, it is more than 2 and less than 5. Cool. So now in a graph, okay, let's say this is 2 and this is 5. Okay, and maybe this is the input 2 and 5. We will have points all over this place. Maybe, okay, these are the points. Okay, so we'll have points all over this place because throughout this this range we have inputs. Okay, so for every point here, for every single point here, we'll have some input. Okay, I mean sorry, some output. Okay, so eventually what you get is you get so many dots. Okay, you get so many dots that you just get a line. Okay, so the point is these continuous functions you'll see as a line as the graph. Okay, as opposed to when you looked at the earlier case, for discrete functions you only see points, right? You see individual points, but for continuous functions you will see lines. Okay, so I think we are done. We already went to 19 minutes, so we'll go for the next video in like not too long from now. So I hope you have a great week and stay safe. Do be excited about domains, codomains, and so on, because domains and codomains are going to be very, very, very important for you, especially when you go into higher level. If you want to major in math, understanding these things are very important. Okay, so yep, see you. Until then, stay safe. Bye.